Welcome back to the session. Is it audible to all of you?
Yes.
Session 4. Okay. Here. Just have a look on the stress versus strain diagram for mild steel, cast iron, and aluminium. Okay. So we had a discussion on stress versus strain diagram for mild steel. Now we need to discuss about cast iron and aluminium. Just draw this figure. Draw that figure. Okay. Can I continue? Here, this will be draw the figure carefully. Now, which color we can choose? Color, that's enough. Okay. Now, this is how much? Theta aluminium. Then from here to here, it will be theta cast iron slope. Okay. This is cast iron. From here to here, theta aluminium. Sorry. Theta mild steel. Is it clear? This is mild steel. Okay. From here to here, here to here, cast iron and aluminium. What you observe from here, tell me now. Here, theta mild steel will be greater than theta cast iron greater than theta aluminium. Correct na? Theta mild steel is greater than cast iron greater than aluminium. Once you apply tan theta mild steel will be greater than tan theta cast iron greater than tan theta aluminium. Okay, so that means slope of the mild steel, slope of the cast iron, then finally slope of the aluminium. What is meant by slope? Slope of stress versus strain diagram is nothing but Young's modulus E. Here, this is E mild steel. E mild steel will be greater than E cast iron. E cast iron greater than E aluminium. Okay, that is the slope now. Slope means slope in the sense slope equals to stress by strain. This is nothing but Young's modulus of elasticity. This is sigma and this is strain. This is strain. Is it okay? Understood up to here? Class lo class. Is it okay? Is it okay? Please respond. Please respond.
Yes, sir.
Yes, sir.
Okay, now good. Here we know that E to E equals to stress by strain. Stress by strain. Sorry. E equals to stress by strain. This is nothing but stress is nothing but P by A load per unit area of cross section. After that, delta L by L. Okay. So then we can say here P by T L by A into delta L. Finally, see this. Okay. Finally, elastic deformation. Elastic deformation. Elastic deformation delta L is nothing but, tell me what is elastic deformation here? Elastic deformation, tell me. P L by AE.
AE, sir.
Okay. So PL by AE is nothing but elastic deformation. So delta elastic. Okay. So delta elastic. This is elastic deformation. Okay. So finally, this is the thing. Now from here, we need to play the game. In what manner we are playing the game, just have a look on it. Okay, beautiful. So now, I think you understood this. Oh, sorry. What is this? Oh man, good. Understood? By using this diagram, you understand. Now, what are the values? Tell me. What are the values? E, mild steel value, tell me. E, mild steel equals to generally 200 or 210 gigapascal. Generally, people will give 210 or 200. There are so many steels now. That is why. So mild steel, there are different types of cast iron also, gray cast iron. Okay, modular cast iron. There are so many cast irons. We cannot give exact value, but it is around 110. Generally, in exam, they use it to give 100 gigapascal. After that, E aluminum equals to, this is around 70 gigapascal. Here, higher the Young's modulus, higher will be the elasticity. Okay? Which one is more elastic? Tell me, among these three, which one is more elastic? Which one is more elastic? Mild steel is more elastic than cast iron, and cast iron is more elastic than aluminum. Higher the elasticity, okay, higher will be the modulus of elasticity. Okay, Young's modulus will be higher for more elastic material. Okay, that is the logic. Here we need to observe one thing. Once you observe here, elastic deformation. Among these three, which one is having more elastic deformation? Anyone please tell me? Mild steel, cast iron, aluminum. Among these three, which one is having more elastic deformation?
Aluminum, sir.
aluminum is having more elastic deformation. Correct na? From here to here, more strain. Okay, strain in the sense elastic, normally strain in the sense deformation, elastic deformation by original length. Okay, so if mild steel, cast iron, aluminum all are having same original length, in that case aluminum is having more elastic deformation compared to cast iron, and then cast iron is having more elastic deformation than mild steel. Okay, so here deformation in the sense elastic deformation, elastoplastic deformation, and plastic deformation. Okay, so that is total deformation. In that case, which one is having more total deformation? More total deformation, mild steel. Okay, so mild steel is having more total deformation, but elastic deformation will be lesser compared to the cast iron and aluminum. That part we need to derive. Okay, here see this. You have written na, up to here is completed. You have written, right? Written or not? Please tell me.
Yes, sir.
Up to here written na, completed.
Yes, sir. Yes, sir.
Now come here. Here. Oh man, we need to select a pin to each and every slide. Good. Now just have a look on this. Yeah, elastic deformation, delta L equals to EL by AE. Here that means delta L is inversely related with the elastic modulus. That means here E mild steel will be greater than E cast iron, greater than E aluminum. In this case, delta L mild steel will be less than delta L cast iron, less than delta L aluminum. Is it clear? Is it clear or not? Simple only na. Just we used one formula and then delta L inverse related with the E. Now from this here, now we can write total deformation. Total deformation. Total deformation equal to elastic deformation plus elastoplastic deformation plus plastic deformation. Okay na? So here my cast iron and aluminum having only elastic deformation. Okay, so even though elastic deformation of mild steel is less than elastic deformation of cast iron. Cast iron. It is one of the good question in competitive exams. Elastic deformation of the mild steel will be less than cast iron, but come to the total deformation. Okay, so here we can say elastic deformation of cast iron is far less than the elastic deformation of sorry here you can write in this case plastic deformation of mild steel. Correct or not? From figure you can see. Yeah, in this case, plastic deformation will be very high compared to elastic deformation of cast iron and aluminum. To get total deformation, we need to add elastic deformation, elastoplastic deformation, finally plastic deformation. That is why we can happily write. We can write this. Okay? We can write total deformation. This is the total deformation of mild steel. Total deformation of mild steel will be greater than the total deformation of cast iron. Okay, so coming to total deformation, mild steel is having more deformation. Okay, na? So total deformation of the mild steel will be greater than the total deformation of cast iron. Okay, so coming to this na total in the total deformation, I think first one is mild steel, second one will be aluminum, finally cast iron. That is correct. So coming to this total deformation of mild steel will be higher than the total deformation of aluminum, total deformation of cast iron. Okay. Why so? Tell me. Elastic deformation of cast iron will be less than the elastic deformation of aluminum. In that case, total deformation of cast iron will be less than total deformation of aluminum. Okay. So in that case, aluminum total deformation of aluminum greater than the total deformation of cast iron. So this is all about elastic deformation and total deformation. There is no plastic deformation for this particular thing. Okay, this is perfectly elastic. There is no elastic plastic deformation for these two. This is all about stress versus strain diagram for mild steel, cast iron, and aluminum. Any doubt so far? Any doubt? These two are very important questions. Which question is asked in the exam? Just have a look on it, whether they are talking about elastic deformation or total deformation. Accordingly, we need to click the answer. Why elastic deformation of mild steel? Okay, now elastic deformation of mild steel is less than cast iron and less than aluminum. You should know. Okay? Clear now? Understood? Yeah. Understood or not?
Yes, sir.
Here you can write a beautiful statement. We already discussed, right? Elastic deformation of mild steel will be less than elastic deformation of cast iron, less than elastic deformation of thus aluminum. Okay, so it is very, very important. Now coming to one more good point here. What? Yes, steel and this is important. This point is important. And generally deformation comparison, mild steel and cast iron. Mild steel is ductile material, cast iron is a brittle material. Okay. So in entire strength of material calculations, we are focusing on mild steel and cast iron. That's it. Now tell me, steel and rubber, which one is more elastic? Tell me. Steel and rubber, which one is more elastic? Steel is more elastic than rubber, or rubber is more elastic than steel? Anyone?
Steel is more elastic than rubber.
Here, among these three, which one is more elastic?
Mild steel.
Why? Why?
The ink smallness is very high.
What?
It has a higher ink smallness.
Okay. Why ink smallness?
Because even if we give more stress, the strain will be comparatively low than other.
Sir, for higher stress, sir, the change in deformation will be low. So, which is in turn, the ink smallness is high.
Good. I am expecting exact point. Because of lesser elastic deformation, high ink smallness you are getting. Okay, now lesser deformation in the sense it is more elastic. Why? Because lesser the deformation, the ease of coming back to original position will be more. That is meant by elasticity. The ease of coming back to original position after removal of the load, that is called elasticity. Lesser the deformation, more chance of coming back to the original position. More chance means higher the elasticity. Understood now? Understood?
Yes, sir.
Lesser the deformation, more chance of coming back to original position, higher the velocity, and lesser the deformation, mathematically high Young's modulus. That is the thing. Lesser the deformation, higher will be the Young's modulus. Higher the Young's modulus, higher will be the elasticity. Understood? Understood? Everything unique points. You won't get this much these points from normal textbooks. Okay, I think it is a wonderful discussion. So first we have drawn these three diagrams. After that, we are observing the angles. Theta aluminum, theta cast iron, and theta mild steel. Then we have observed it. Which one is more? You found that mild steel is more. Okay, na theta mild steel, theta cast iron and aluminum. Applied tan, then you got the slopes. Slope is nothing but Young's modulus. Then we have drawn Hooke's law. From Hooke's law, you got elastic deformation. From that expression, we have written. Okay, na. So E mild steel, this result you got already. You got it. Just applied here and elastic deformation you are getting. Someone messaged me, but rubber is more elastic than steel. Why rubber is more elastic than steel? Who said rubber is more elastic than steel?
Because lesser deformation. Because of lesser deformation.
That we can see now. Yeah. Before that, just have a look on the stress versus strain diagram for different materials. Okay. Tell me, is it what is the here stress versus strain diagrams are drawn? You need to say the names. Please tell me the names. Please. This diagram is drawn for what? Stress. This is sigma and epsilon. It is also sigma and epsilon. Sigma, epsilon. Think about it and draw all the figures. Sigma and epsilon. Sigma and epsilon. It will come like this and coming back. Now tell me, This diagram is drawn for which material? I'm asking. This diagram is drawn for which material? Tell me. Anyone, please tell me.
Stress constant. Sorry.
Yeah. Which material I'm asking? Which material? Which material? Here we are applying the load. Load increases, okay, and stress also increases, but deformation is 0. That is the meaning of this figure. Even you apply infinite amount of load, but there is no deformation. No deformation means no
rigid material.
Then we can call it as a
Rigid material.
okay, so this is nothing but rigid. Okay, this is for rigid material. Perfectly rigid. This is, tell me, this diagram is drawn for what? Perfect elastic. This diagram is drawn for perfect elastic material. This drawn for perfect, tell me, plastic, correct or not? Perfectly plastic. This is rigid means perfect rigid. Perfect rigid. This tell me. Please tell me. This diagram is drawn for what? Elastoplastic. Okay, perfect elastic and elastoplastic. Here it is also elastic and plastic. Elastoplastic or elastic and plastic with unloading. This is unloading. Okay, here you can say load is here. Generally, here it should not be strain actually. Velocity gradient will be there. Okay, dou u by dou y. Here stress is nothing but tau. This is nothing but. Now tell me. Rate of shear strain. Okay. So now tell me what is the name of this particular thing? What is the name? Tau, shear stress, and tau u by tau y, velocity gradient. This is nothing but ideal fluid. Okay. So this is all about stress versus strain diagram for different materials. Okay, so this is for ideal fluid. Okay, so perfectly rigid. In this case, deformation is 0 here. This is deformation is 0, and here stress is directly proportional to strain. And here stress is constant. Elastic and plastic. Plastic with unloading. It can't reach to here. Elastic in the sense with unloading exactly will come to here. Okay, that is meant by elasticity. Okay, ideal fluid generally tau and velocity gradient. That's it. Any doubts so far?
So example for all this.
What?
Examples, real life examples.
Real life examples.
Example materials, yes.
What?
Yes, sir.
Perfect rigid in the sense that is just assumption. Okay, no material is perfect rigid. Generally, we are having rigid in the sense rigidity itself is an assumption actually. Ideal fluid also assumption, ideal cases. This is also ideal case. Okay, by assuming this, we are focusing on total engineering mechanics calculations now done based on this assumption. Okay, all materials in the engineering mechanics course non-deformable bodies. Okay, that is perfect rigid, and perfectly elastic means cast iron, and it is also not exactly perfect actually. Okay, perfect plastic material in the sense it is one type of rubber type thing, perfect plastic. So to manufacture this particular by robotics now. Okay, so in that robotics field, people use plastic materials, rubber type thing, different types of rubber. Okay, I think based on the number we can differentiate it. Elastoplastic and viscoplastic, like that. Plastic materials. Unloading is different. It is an operation. That's it. Okay, understood?
Yes, sir.
Perfect elastic examples we cannot say. Why? Because material is not perfectly elastic. Perfect rigid material is not exist actually. Okay, once you apply the load, some deformation will definitely there. For calculation purpose, you are taking it as an assumption. Okay, understood. This is mechanics of non-deformable bodies. Study of non-deformable bodies or study of rigid bodies, mechanics of rigid bodies. But our course is what? Mechanics of deformable bodies. Okay? Strength material na solid mechanics. All bodies will deform when you apply the load. Ideal fluid, this is related to fluid mechanics course. This is not related to strength material. Just vertical line is there, and inclined is there, horizontal is there, and again it is coming like this. Why not why not a line on x-axis? That is the idea. In that case, ideal fluid is coming, but we need to change it. That's it. No need to study this part in the strength of material course. Now tell me why steel is more elastic than rubber. Anyone please tell me why steel is more elastic than rubber? First, tell me, steel is more elastic than rubber or not? Please tell me. Steel is more elastic than rubber or not? More elastic than rubber. First, draw these two figures. First, draw these two figures. Draw these two figures. Okay, na? Can I say? It is L0. Original length is same for both the cases. Okay, na? Original length is same in both the cases. This is, sorry. Yeah. Final length. Final length, L final for steel. Okay. This is for steel. This is for rubber. Final length of the rubber. You can say dash rubber. Okay. This is for rubber. Can I say it is steel? First to draw this figure. You can understand, no issue. It is simple logic only. I think you must have studied this thing very long back, around 10th class or before 10th class. It is steel actually. It is steel. I must have changed the color. Steel, rubber color is different. No issue, no time. It is rubber. Okay? It is steel and it is rubber. Okay, so once you apply the same load, here you applying P, here also you applied P, same load, and same area of cross section, same area of cross section here and here. Okay, A steel, A rubber. Okay. So area of cross section of the steel equivalents to area of cross section of the rubber. In both the cases, you are applying same load. Okay. So for example, L naught equivalents to maybe 250 mm. 250 mm. Okay. So here L naught, both L naughts are same. 250 mm you are taking in both the cases. A steel, you are taking 100 mm square, maybe 100 mm square, and A steel or A rubber also 100 mm square. Okay, 100 mm square. After that, load also same. Load equal to 10 kilonewton. Here also load equal to 10 kilonewton in both the cases. So here, can you observe it? L final in the steel will be less than the L final of the rubber. Is it correct or not? Just take a feel. Just feel it. Both are same specimens. Same specimens. Again, rubber will deform more, na? More deformation will observe in the rubber. Rubber or steel, tell me, just feel it. You are having one mild steel or mild steel rod and rubber. Same cross section, same length, but different materials. Okay. So now you applied the same load on both specimens. Which one will deform more? No, without doing experiment, are you able to say rubber will deform more compared to steel? Correct na? Correct or not?
Yes, sir.
So here delta steel will be less than the delta rubber. Correct? Correct or not? Yeah, delta steel is nothing but L final minus L naught. Okay? Here delta dash rubber equivalents to L naught. Sorry. L final dash minus L naught. Okay? So that is the thing. Now we can say delta is nothing but load into PL naught. Okay now, PL by A E na. Okay, if it is rubber, you will get this. It will be rubber and E rubber. Here delta steel. Okay, dash you can take. Delta steel is nothing but in both the cases you are taking same load and it is also same PL naught original length na PL by original length taken A steel and E steel. Here PL by A is equal to constant. Correct na? Constant or not? Then we can say here delta will be inversely related with E. Remaining three are constant. Delta will be inversely related with E. So from these calculations, can I proudly say elastic modulus of the steel. Okay, elastic modulus of the steel will be greater than elastic modulus of the rubber. Is it correct or not? Correct or not? Anyone having a doubt in this? Anyone having doubt here? Please respond.
Sir, can you repeat, sir, once again, please?
From where? From where?
That last point, sir.
This. Which one you are not getting? Tell me. This you understood? First, see two specimens. Okay. Both here one is made up of steel, another one is made up of rubber. Of course, this is initial. This is initial dimensions, and the yellow color is after deformation. Nah, it is final dimensions. Initial original length is same in both the cases, and L final steel is here. L dash final rubber. Just a common sense. Same specimen and same length, area of cross section is same. You applied the same load. Of course, rubber will elongate more compared to steel. Will you believe it or not? Will you accept it or not? Of course, yes, sir. L final rubber will be higher than the steel. Okay, L final steel is less than the L final rubber. I think this thing you understood. This part you understood.
Yes, sir. Yes, sir.
Right?
Yes.
So just to see this delta steel in the sense like this, na delta steel in the sense L final minus L original. Here also same L dash thing, L final dash L naught minus L naught. So here L naught is same in both the cases. Then elastic deformation of the rubber is higher. Okay, just I took elastic deformation of the steel and rubber. P is constant and L naught is area of cross section is same. From there I built delta inversely related with E. That means okay, delta steel is lesser. That means Young's modulus of the steel will be higher. Higher the Young's modulus, higher will be the elasticity. That is why steel is more elastic than rubber. Okay, one more explanation here is lesser the deformation. Here deformation is lesser, na more chance of coming back to original position. Higher the deformation, okay, lesser the chance of coming back to original position. Okay, the ease of coming back to original position is nothing but elasticity, and in that case lesser deformation, that means steel will come back to original position faster rate compared to the rubber. That is why steel is more elastic than rubber. Is it okay?
Yes, sir. Fine, sir.
Now, next, I think this is the first topic. Okay, first topic in the first chapter. Now we need to start a new topic or else new chapter. Okay, first chapter is completed. Strength of material course. First chapter is stress versus strain diagram. In that, first topic is completed. Now we need to discuss second topic. Okay, are you okay with this? Are you okay?
Yes, sir.
Now we need to discuss the second topic. Put heading. Axial loading diagrams.
Sir, can you repeat the last slide, sir?
Which one?
This one, sir.
Which one?
Steel versus rubber.
What?
Steel versus rubber, sir.
Steel is?
Steel versus rubber. This slide, sir.
This
Can you
slide.
repeat once?
From the beginning.
No, sir.
What is your doubt, tell me?
Actually, which is more
You are
elastic?
not able to convince.
No, sir. I just went out, sir, for 2 minutes, so I didn't catch this point.
Okay, good. Okay, fine. Here, this is steel specimen. This is rubber specimen. Okay. So initial length is same. Original length L0 same cross section. You applied the same load. You tell me. You applied same load, steel or rubber. Which one will elongate more? Tell me. In which specimen will elongate more? Please.
Rubber, sir.
Rubber will elongate. That thing I have written. L final steel less than L final rubber. Elastic deformation in the sense L final minus L naught, L final minus L naught, correct? So higher the elongation, higher will be the elastic deformation, correct? Change in length will be higher. Why? Because both are having same original length. Higher the elastic deformation, lesser will be the Young's modulus. Okay, in this case, steel is having lesser lesser elastic deformation. That is why it is having more Young's modulus. So higher the Young's modulus, higher will be the elasticity. In that case, steel is more elastic than rubber. If you face same question in the interview, you need to give this much explanation. Okay, now don't directly give steel is having more Young's modulus compared to rubber. Don't say like that. Okay, that is not elastic property. Elasticity means the ease of coming back to original position. Okay, lesser the deformation, higher will be the chances of coming back to the original position. That point interviewer will expect, not the values. Based on the values, how can you say? Okay, fine, you are having one statement, higher and smaller, but that is not exact explanation. Elastic, more elastic means first what is meant by elastic you need to explain. What is meant by elasticity? Elasticity is a property of a material. Okay, coming back to original position after removal of the load. That point should come in the explanation. Otherwise, you are a mug-up candidate. Like that interviewer will feel. Understood? Understood now?
Yes, sir. Yes.
Now, next, put it in. Put it in. Axial loading diagrams. Reading axial loading diagrams means ALD. Axial loading diagram means ALD. Axial loading diagrams. Write down the objective. Write down the objective. Okay. First write up, keep there. Start in the new page. That is must. Okay. Start in the new page. Okay. Put it in. Write down. To determine axial stresses, the member or bar, and axial deformation at a point in statically determined or statically indetermined. Statically determined or statically indetermined, comma, or else prismatic or non-prismatic composite prismatic composite or compound bar. or compound bar is a compound bar which is subjected under undetermined or undetermined, statically indetermined, and undetermined, indetermined, subjected under uniform or non-uniform axial loading conditions. Axial loading. Okay. Have you written? Tell me. Is it okay? Completed? Completed or not?
Yes, sir. Yes, sir.
Okay. This is the very beautiful statement. Okay. So from this objective, you will complete everything actually. To determine axial stresses. Okay. Axial stresses in the members. Okay. Axial stresses in the member. Now that. Okay. So or else you can change the color. It is very important. And axial deformation at a point. Okay, it may be 1 hour class or 10-hour class. Final aim of the thing is axial stresses in the member and axial deformation at a point. In a statically determinate, what is meant by statically determinate and statically indeterminate? Okay, na? So you should know the meaning of the statement. Meaning of the statement. Which one is? Yeah. So what is meant by statically determinate? What is meant by statically indeterminate? Prismatic or composite compound bar, which is subject under uniform and non-uniform axial loading. You should know the meaning of each and every term. Your life will be cool. Clear na? Understood? Total, complete chapter, complete 10 hours of discussion covered here. Around 10 hours, more than 10 hours of discussion covered here. Oh, so more than 10 hours of discussion is covered here. Anybody having doubt, tell me. Anybody having doubt here? In this objective, you will focus on axial stresses calculations, axial deformation calculations. Axial stresses in the member, axial deformation at a point. In the statically determinate, statically indeterminate, prismatic, composite or compound bars, which is subject under uniform or non-uniform axial loading condition. Here, what is meant by, just have a look on it. Here, what is meant by statically determinate? That is important. Statically indeterminate. Prismatic composite compound bar. What is meant by composite bar and compound bar? And uniform axial loading, non-uniform axial loading. First, what is meant by axial loading? Okay. Is it clear? At least terms you are observing now. What are the things need to be done for next 6 or 7 hours? This is the objective. Is it okay? Is it
Okay, sir.
Fine, sir. Fine.
procedure to draw axial loading diagram? See here. First, have a look on the diagram. Axial loading in the sense like this only, na? First, draw this figure. First, draw this figure. I will tell you how to draw axial loading diagram. Okay? Where, chef? Take. Is it okay? First, draw this figure. Assume that it is a prismatic bar. Assume that it is a prismatic bar. And it is fixed one.
What does mean by prismatic bar, sir?
Uniform area of cross section. Okay, it is having uniform area of cross section.
Okay.
Prismatic bar. Perfect. We can use this now. Okay, so it is subjected under uniform axial loading. The load P is acting here. Okay. It will be P. What happened to this? Take, it is load P is acting here. Now draw this figure first, then I will explain. Okay. So one diagram is enough, then you can happily understand the things. Now here it will come down. Okay. After that here, next we need to draw one line here to draw axial loading diagram. Okay. Okay. Yeah. First to draw these lines. Are you using scale or not? Huh? Anyone using scale? Okay. Good. Now I think total all the diagrams will be over by one logic. That logic we are going to discuss. Okay. Here, which color is better? Got it. No. Yeah. Is it fine? Now how to draw the diagram? Is it clear to all? Axial loading diagram. First we need to draw first observe it, then we can start drawing figure. So here load is acting here is, the load which is acting here is P. Load acting here is P, and then here it is fixed actually. Now can I say area of cross section, length in length will be L, area of cross section will be A, and E will be the Young's modulus, A comma E. Okay, so AE is nothing but axial rigidity. AE is nothing but axial rigidity. Observe it. See. Hello? Are you there? This is point A. This is point B. Point B. Here also point A and point B. I am trying to draw axial loading diagram. Is it okay? Anybody having doubt up to here? Please tell me. It is a simplest one. Okay, one bar subjected under axial loading. You are trying to draw axial loading diagram. Okay, now what is the first step? All are there na? Anyone went for outing? All are there? Please respond.
Yes, sir.
All are there na?
Yes, sir. Yes, sir.
Okay, this 2 minutes of discussion is very important. Then once you understand this procedure to draw axial loading diagram, you will be in the track. Okay. So whatever the procedure I am following here, same procedure I will follow for all the diagrams. Axial loading, SFD, and BMD, TLD. Total 4 diagrams, 8 marks. Observe it. Observe here. First step. Take sign convention. Okay. Now, in axial loading diagram, sign convention is what? What is the sign convention? What is the sign convention? Tensile positive, compressive negative. Okay. Start from one end, finish at the another end. Start from one end, finish at the another end. So here I am taking sign convention. Okay. Outside force assumed to be positive. Correct now? Here the force which is acting away from the bar, the force which is acting away from the bar, okay na, that force is assumed to be positive. Correct? Correct or not? Please respond. The force which is acting away from the bar, outward, that is positive. Outward means tensile positive. Forget about the remaining loads. Focus only on the one load which is acting at right end of the right or left end of the thing. Now here sigma h equal to 0, reaction will come here. What is RA? Tell me. What is the reaction RA? It will be P na. Correct or not? P na. Now start from here. Start from here. What happened to that? Start from here. Now I am here. Now I am here. I have seen the load. Both are acting in the same direction or opposite direction. Anyone please respond? Please respond. Now I am
Opposite.
I have seen the load. Both are acting in the same direction or opposite direction.
Opposite.
Direction or opposite direction. Same direction. Okay. So then same direction means positive or negative. Positive means you need to move up or down. We need to move up. So here we need to move up.
Sir?
Up by P. Correct?
So what is the line AB, sir?
Line AB, just one horizontal line. Just one, draw one line AB. Okay. It is common in all the diagrams. SFD, BMD, and all the diagrams. First you need to draw one line. Okay. Is it okay?
Then you talked about the two forces, right?
It
The
is a
direction of the
reaction force. It is a reaction force at the fixed support.
No, sir, you talked about the B line force. I mean the positive you wrote there.
P is nothing but external load, applied load, axial load. It is axial load.
Below that.
Hmm?
Below that. AB line. Yeah, AB line you wrote positive, right?
Axial load. This is loading diagram. You are representing the loads in this particular diagram. Okay. Now I am here. I have seen the load. Both are acting in same direction. Same direction is positive. Positive means we need to move up by P na. That
Yes,
this much of load is acting at this point. That is the meaning of this. Okay. You are representing all axial loads in this particular diagram. Correct?
Yes, sir.
Okay. So now I am here. I have seen the both are acting same direction means you need to move up by P. If a prismatic bar, whatever the bar it is, okay, now subjected under only axial loads, axial loading diagram will be rectangle. Only shear force diagram will be rectangle. Only shear force means point shear force. It is point axial load. For all point loads, corresponding diagram will be rectangle. Corresponding diagram will be rectangle. Don't lift your pen until and unless next load came. Until and unless next load came. Correct na? Don't lift your pen until unless next load came. Now I am here. See this. Now I am here. I have seen the load. both are acting in same direction or opposite direction from right side. Same direction or opposite direction? Tell me. Now I am here. I have seen the load. Both are acting in same direction or opposite direction from right side. Opposite direction, na? Please respond. Otherwise, how can I understand whether you are following or not?
So the left side of the bar is, it is placed, right?
Hmm?
Left side of the bar is placed to something.
I'm not getting actually. Actually, here we need to start from one end. It is first problem. Na actually same kind of words. I think a total strength of material this only. Okay, no need to worry. You will be in the track. Okay, start from one end, finish at the another end. Follow one sign convention throughout the diagram. Okay, so here tensile in the sense outward force assumed to be positive. Start from here. And now I am here. I have seen the load. Okay, now both are acting in same direction means we need same direction is positive. Positive means we need to move up. Okay, so only point axial loads, axial loading diagram will be rectangle. Don't lift your pen until unless next load came. Okay, now next load you are seeing. Next load is this. Now I am here. I have seen the load. Both are acting in opposite direction. Opposite direction means we need to move. Opposite direction is negative. Negative means you need to move down. Down by P. That's it. Okay. Down by P. Anybody having doubt, tell me. Anybody having doubt, tell me. Anybody having doubt? Oh, here it is gone. Oh man, total thing gone. No issue. Okay, so here what will come, tell me? From here to here. Okay, try to draw by your own. Here what will come? From here to here, we need to move up. After that, up to here, what will come? Tell me. This is the figure. Up to that, this diagram we need to draw. Okay. Then we need to move down by P. We need to move down by P. This is the diagram. Correct. So just to see this is the diagram. Just to draw the thing. First to draw this figure. Okay, it is fixed one. Here load P is acting. So once you take this na, here this particular reaction force at point A is nothing but P. It is A point. Of course, it is A point. This will be B point. Length will be L. Here area of cross section A and Young's modulus will be E. Okay, so you started this particular diagram AB. You assumed one now. Okay, this is the assumption you made. This is P actually. This is of course positive. Okay, na? So in this direction you assume it to be positive. Now I'm here seeing the load. Both are acting in same direction. You need to move up. Don't lift your pen until unless next load came. Now I am here. I have seen the load. Both are acting in opposite direction is negative. Negative means you need to move down by P. Throughout the bar, it is subjected under P and it is positive. Now, what is the axial stress? Axial stress in the member AB. That is our job, na? Axial stress in the member AB. Here it is statically determinate or statically indeterminate? Statically determinate or statically indeterminate? Anyone please tell me? Static
What do you mean by that, sir?
determinate means here statically determinate means one end is fixed. Statically indeterminate means both ends are fixed. Okay, so that I will tell you. Here number of unknowns one RA, only one support you will get horizontally. Here we need to apply sigma H equal to 0 equilibrium equation. Okay, na? Sum of the left force equal to sum of the right forces. That is why RA equal to P, you will get it. Madan raised hand. What is the problem? Tell me.
So what is the, sir, if the load is acting in the opposite direction, what will happen, sir?
Load is acting inward, na?
Yes,
Inward in the sense we need to assume this direction.
as negative.
And here I have seen the load, both are acting in opposite direction. Opposite direction, negative means you need to come down.
I generally assume, sir, horizontal right rotation is opposite, horizontal left rotation is negative. Can I assume like this, sir?
No. A load which is acting away from the bar. Load is pulling the bar. Pulling
Okay.
to be tensile.
Near the means it's compressible, it wasn't negative.
Yeah, but you need to assume one direction. Otherwise, towards assume to be negative. Towards, okay, if you assume, no issue, nothing wrong.
Yeah, okay.
Here, this thing assumed to be negative. Okay,
Yes.
now here I have seen the load, both are acting in opposite direction or same direction? Opposite. Opposite
Yes,
is positive, na?
yes, sir.
Opposite to negative is positive, right? That is confusion, correct? So better to assume positive things. This is positive, correct?
Yes.
Understood. Just assume this direction. I think for around 7 hours, you will follow the same procedure.
Yes.
Within 1 hour, you will be in the track, no issue. Same words. Assume this direction, start from here, see the load, both are acting in same direction, opposite direction, same. Same means move up, opposite means come down, and come up to here. Any load which is acting here, then accordingly you can act now. Understood?
Yeah, yes, sir.
Not. Okay. Is it okay?
Yes, sir.
Good. Now. So this is the way. Now, sigma AB, tell me. Load acting in the portion AB. Load acting in the portion AB. Area of cross section of the portion AB. Is it correct or not? Correct now? Okay, now what is the load acting in the portion AB? From axial loading diagram, you will get it. From axial loading diagram, tell me what is the load acting in the portion AB? P, na? Correct or not? P.
Yes, sir.
Okay. You will see the load here and length here. Okay. Load versus length diagram. Load versus length diagram. Load you will see on y-axis. Length you will see on x-axis. What is the load acting on this in the entire portion? P, right? P or not?
Yes, sir.
By area of cross section A. Area of cross section A is nothing but pi d square. 4p by pi d square. You will get it. Correct? So now, what is the axial deformation at point B? What does it mean? Tell me. Axial deformation at point B means what? Axial deformation at point B means what? With respect to point A, we need to write. Axial deformation at point B is nothing but axial deformation at point B with respect to fixed end, you need to write. With respect to fixed end means PL by AE, PL by AE in the portion BA, we need to write. What does it mean? Tell me. P will come, length will be L, area of cross section is A. It is simple problem, na? Basic, that is why you are writing it. This is total deformation. Correct, na? Only one bar, right? We can call it as a total deformation. Sorry. It is total deformation. Total axial deformation. Okay? Only one bar. Understood, right? Understood or not? Okay.
Yes, sir.
Now see the thing. Now we will go to the next logic. Just to see this. I will give you the figure. Sorry, what happened? Now I will give you a different case. Axial loading diagram only. Okay. So here I will give you the different figure. Okay. Now we need to draw the figure actually. That is our task. Okay. Now here one load will be acting here. One load will be acting here. Instead of writing on the board, better to draw here. It is simple. You will get exact same thing. Okay. Now here we can apply one more load. It is compressive in nature, not compressive towards that. Okay. Next, one more load is acting here. Okay. One more load is acting here. Now we can say that numbers here one member, but this is another member. Maybe here you can keep equally, and this member will be somewhere here. Okay, all are having same length. That is better. One more load is acting like this. Is it okay? Understood now? You got the figure? Got the figure or not?
Yes.
First draw the figure.
One end fixed or not, sir?
Yeah, of course, one end is fixed. Okay? One end is fixed. Now we can draw the figure in a comfortable manner. Here you will get, first draw these kind of lines. Draw this kind of lines. After that, in the same manner, we can draw the figures. In complete, in all the cases, we need to draw SFD, BMD, whatever it may be. You need to follow the same. Okay? Is it okay? Is it okay? Now, once here it will be, here you can say P is this. Here you can take 4P. Understood? Then here you can keep 2P. And then here you can keep P actually. P. Then or else you can keep to 3P within 3P. And here it will be, how much you can keep? 2. It is 2P. Okay? Is it okay now?
Is it given or we assume, sir?
What?
4P, is it given or we shall we assume, sir?
Just given.
Yes.
Gave it. It is given, not assumption. It is a question. This type of questions you will see in the exam. Is it
Sure.
okay? This type of questions you will see in the exam.
Sir.
Okay. Understood?
Sir.
How to draw the diagram. That is the game. How to draw axial loading diagram for this. Okay.
Sure.
Tell me.
How does
How to draw axial loading diagram.
sir? How does the load act internally to along the axial line, sir?
Super
Internal
man.
to the bar.
You are excellent, really. I will tell you. Generally, for first class itself, you asked the doubt. Na? Great. What? How the load is acting internally. Correct, right? That is
Yes, sir.
na, Kelvin?
Yes, sir.
Super. Generally, this is really superb doubt. No one asked in the class. I only asked the question. I only explained that question in all the batches. Super question. Seriously. I think I will tell you. It's a wonderful question. Some discussion is there. I will tell you. Okay, na? I will tell you that. Actually, in all the batches, after completion of 6 or 7 hours, I will ask the question. I will ask the doubt actually. Here, you people blindly drawn everything. Na? No one asked a question like, here load acting here. I think external load is acting here is possible. You can apply by some means. But you should ask a question like, okay, how the load can be applied at this point? Okay, now we solved minimum around 60-70 problems, but no one asked that kind of question. Like that, I will tell at the end of the class. But you asked in the first class itself. Good. Okay, I will tell you at the last. No issue. Okay, now
Okay, sir.
don't forget about everything. Here, this kind of figure will be given. This kind of figure will be given. For that, you need to draw axial loading diagram. Okay, axial loading diagram. Now, see this? Here, what is the reaction? First, calculate the support reactions. It may be SFD, BMD, whatever it may be. What is the support reaction RA? Anyone please tell me? Here only one equilibrium equation. See, sigma H equals to 0. Sigma H equals to 0 means sum of the left force equal to sum of the right forces. Left forces
RA is equal to 4P.
RA plus 5P na?
Yes, sir.
Equal to 6P na? Correct? Finally, RA is equal to P na? Any doubt? RA equal to P, right? Tell me.
Okay, sir.
From here to here it is L. Here to here it is L. Here to is L. It is also L. Okay? Here you can take A, B, C, D, and E. Our game here is, it is A, it will be E, in between, this will be B. 1 minute. Here, what you will get, tell me? Here you will get this kind of line. Draw this kind of dotted lines. Straight line we need to draw now. Okay. I think better to keep this thing here. Okay, you will get a more space. No issue. Okay. Is it okay now? Is it okay? Okay. So first you need to select the pen. Don't worry. Slowly we'll get it. Here, assumed this direction as positive. Okay. This will be A. This will be E. What is the first step? Tell me. Start from here. Correct? B. It will be C. It will be D. Start from here. Start from here. I have seen the Lord. Both are acting in same direction or opposite direction. Same or opposite?
Same direction.
Same means positive or negative.
Positive.
Positive means we need to move up or down.
Up.
We need to move up. Move up by 4p. Is it okay? Is it okay?
Yes, sir.
Don't lift your pen until and unless next load came. Until unless next load came. Now I am here. I have seen the load. Both are acting in same direction or opposite direction. Same or opposite? Tell me. Start.
Same direction, sir.
Both are acting in same direction or opposite direction.
Same direction.
Same opposite, man. Yeah, arrows. Both are acting in same direction or opposite direction.
Same, sir.
Same means positive or negative.
Positive.
Positive means
Upward.
you need to move up or down.
Upward.
Up by 2p means 6p na.
Yes, sir.
Don't lift your pen until unless next load came. Okay, it is 6p. Now I am here. I have seen the load. Now I am here. I have seen the load. Both are acting in same direction, opposite direction.
Opposite direction.
Opposite means positive or negative.
Negative.
Negative means you need to move down by 3p means what? Move down by 3p means what? It will be 3p na.
Yes, sir.
6p minus 3p na.
Yes, sir.
Don't lift your pen until unless next load came. It is 3p. Now I am here. I have seen the load. Both are acting in same direction, opposite direction.
Opposite direction.
Same or opposite. Now
So I think no load is
I have
applied.
seen the load. Both are acting in opposite direction. Opposite means negative. Negative means you need to move down by 2p negative. 2p negative means it is p na. 3p minus 2p. Now come up to here. Come up to here. Now I am here. I have seen the load. Both are acting in opposite direction. Opposite direction means negative. Negative means you need to move down. So everything is positive or negative? Everything is positive, na? Positive or negative? Positive. Is it okay? Is it okay?
Okay, sir.
Now I will draw the same figure again. We'll discard it. So I will draw the same figure again. Okay. So first, yes. Yeah, I have seen the load. Wait 1 minute. Is it positive or negative? Tell me, is it positive or negative?
Positive.
Okay. So that means you should understand this procedure. Then your life will be cool. Positive. Okay. This is positive. Clear na? Now, yes. Now I am here. Better to keep this thing at the bottom. A wonderful figure. Okay. Now I am here. Come up to here. Okay. Positive means come up to here. Of course, it is 4p na. 4. And then don't lift your pen until unless next load came. Don't lift your pen until unless next load came. Now both values are same na. Up to this point, load is same. Up to this point, load will be same. Next, now I am here. I have seen the load. Both are acting in same direction means positive. Okay. Oh man. Then diagram will be good, looking good. Okay. Now go up to here. Okay. Go up to this point. Then how much you will get? Tell me. Moving up by 2p means Moving up by 2 means 6p, na? Okay. Is it okay? Don't lift your pen until unless next load came. Okay. This is also 6p. This is also 6p. Then come down here. Now I am here. I have seen the load. Both are acting in opposite direction. Opposite direction means we need to move down, right? We need to move down by 3p. Because it should be below that 4p. Na? We need to move down. We need to move down by 3p. 3p means 6p minus 3p. Okay. Then you will get 3p. Then what to do? Don't lift your pen until unless next load came. Until unless next load came. Okay. So this is 3p. Then this will be 3p. This will be 3p. Now I am here. I have seen the load. Both are acting in opposite direction. Opposite direction means negative. Negative. How much we need to come down? 2p. 2p in the sense 3p minus 2p. 3p minus 2p will be p, na? Of course, p. This will be p. This will be p. Then come up to here. Okay, come up to here. Then that is p actually. Then what to do? Tell me. Now I am here. I have seen the load. Both are acting in opposite direction. Opposite direction means negative. Negative here. How much? P negative. Come down by p. Then your diagram must be complete. Your diagram must be complete. If it is open, na, gone. Your answer is wrong. Not answer. Your diagram is wrong. Is it okay?
Okay, sir.
This diagram is okay, na? Anybody having doubt? Okay. Okay. Is it
Okay, sir.
okay? Understood or not?
Yes, sir.
This will be white. The diagram is perfect. Anybody having doubt up to here? Anybody having doubt up to here?
No.
No, sir.
Now. Don't worry. Next class, you will be in the track. For time being, you can understand. I think you understood now what we did till now. Understood or not?
Yes, sir. Yes, sir.
Here it will be E point. Okay. So this is B point, C point, D point. From this figure, you tell me what is the load in the portion AB? What is the load in the portion AB? Anyone please tell me what is the load in the portion AB?
P.
P. Okay. What is the load in the portion BC? Tell me what is the load in the portion BC? 3P, na?
Yes, sir.
Okay. What is the horizontal line here? Complete BC, 3P, na?
Yes, sir.
Okay, not at the junction. Don't focus at the junction. Throughout the bar. Focus only on that. Okay. PCD is how much?
6P.
PCD is how much? PCD 6P. It is LKG like of discussion. I have drawn the figure. I am asking the load in the portion DE. What is the load in the portion DE? How much?
4P.
4P. Good. Yeah. Now tell me axial stresses in the bar. Okay. First task is axial stresses. What is the axial stress in the portion AB? Tell me. What is the axial stress in the portion AB? Tell me. PAB by area of cross section A, na? Correct? This will be P by A, na? Okay. 4p by pi d square. 4p by pi d square. Now tell me, sigma BC, tell me. Anyone? Sigma BC means PBC by area of cross section. What is PBC? What is PBC? 3p
12 by pi d
area
square.
of cross section. That means 12p by pi d square na. Here area of cross section A means pi d square by 4. Sigma BC and CD. Okay. PCD by area of cross section. What is CD? PCD? 6p by A. 6p by A means 24 na. 24 by pi d square. What is sigma D? What is sigma D? PDE by area of cross section is same, right? What is PDE? 4p na. 4p by area of cross section 16p by pi d square. 16p by pi d square. That is the key. Understood? Understood or not? Among
Yes.
all, which is the maximum tensile stress? Tell me. What is the magnitude of maximum tensile stress in the member? Tell me. Can I say
CD, sir.
maximum tensile stress? Can I say this is maximum tensile stress? Okay. Is it okay?
Okay, sir.
So this is nothing but sigma T maximum. Okay. Maximum tensile stress in the member. Here sigma T maximum is nothing but maximum tensile stress is nothing but how much? Sigma CD, that equals to 24p by pi d square. 24p by pi d square. What is the minimum tensile stress? Tell me. What is the minimum tensile stress? Anyone please respond?
AB, sir.
Yeah. Yeah. Which is minimum? Of course, this. There is no compressive stress. There is no compressive stress. This is sigma T minimum. This is sigma T minimum. That is the thing. So finally, you calculated maximum and minimum tensile stress in the given bar, which is subject under non-uniform axial loading condition. Next, coming to the next slide. Deformations, axial deformation. Here, axial deformation. Wait a minute. Our aim is that only. Remember our aim. What are the things we need to discuss in entire axial loading diagram? Here, delta E. What is delta E? Tell me. Axial deformation. Axial deformation. Axial deformation at a point. Axial deformation at a point E. This is axial deformation at a point E. What I said, tell me. At a point E means with respect to fixed end. That thing you need to write now. Correct. Axial deformation at point E means axial deformation at point E with respect to fixed end. What happened? Where is this? Okay, fine. No issue. Axial deformation with respect. With respect to A. With respect to A, we need to write. So what is this? Tell me, how can you write this expression? Delta EA. How to write? You can rub it. What, man? How to write that expression? Just have a look on it. Yeah. It is very important. All are same. You can solve around 10-20 problems. Sorry. Okay, now what is delta EA? Anyone please tell me? Delta EA equal to delta ED plus delta DC plus delta CB plus delta BA. Tell me. Delta ED, principle of superposition. Delta ED, delta DC plus delta
CB,
DC plus delta
CB,
plus delta BA. Okay. Delta BA and delta AB both are same. Okay. Now, what is the deformation in the member AB? What is the axial deformation in the member CB? The axial deformation in the member DC. Okay. Okay. It is DC. Okay. Understood now? Understood or not?
yes, sir.
We can go through this. Now tell me the expression. Delta, here tell me, delta ED na? Delta DC, delta CB, delta BA. Delta BA. Here tell me, P, what is the load A, PL by AE? PL by AE in the portion ED and PL by AE in the portion DC, PL by AE in the portion CB, PL by AE in the portion BA. Okay, what is the load in the portion BA? Tell me. P na? Correct? Load in the portion BC, tell me, or else CB. Load in the portion CB, tell me. Anyone? You should
Three, sir.
written na.
Three.
What is the?
Sir?
Okay. What is load in the portion CB? Tell me.
3 pieces.
Load in the portion DC. Load
DC is 4 pieces.
ED. You should tell. ED means 6P na? 6P or 4P? I think 4P. First one is 4P na? And then 2 added. 4P and then 3 subtracted. 3P and then 2 subtracted. That is correct. So now here, you people are not writing, I guess. You're just simply sitting in the class. How can you improve na? So here tell me PL by AED in the sense 4P. Length will be same for all. AE also same. Okay. So AE is constant. Here for DC 6P. 6PL by AE. AE. After that CB in the sense 3PL by AE. Okay. Then PL by AE. Finally, what is the total deformation? Tell me. Delta E. Yeah.
14.
Delta E is
14
nothing
PL
but
by
10, 14 PL by AE. Okay. So then what you will get? Tell me. This is the thing. So now tell me delta C, tell me, delta D. Delta DA, tell me. What is delta DA? Delta DC plus delta CB plus delta BA How much you will get, tell me? DC plus CB, BA. These three terms you will get it. Correct, na? These three terms you will get it. DC,
Yes, sir.
CB plus BA. That means you need to add these three terms.
We
How
get 10 PL by
10
PL.
by A, E. Now, delta ED, na? CC. Yeah. Delta C. A. Delta CA in the sense delta CB plus delta BA. How much you will get, tell me? Delta CB plus BA means these two terms you will get it. These two terms. That means these two terms we need to write 4 PL by
4 PL by A.
yeah. Yeah, delta B at this point in the sense delta BA in the sense PL by A. So now tell me which point is subject under more the maximum magnitude of axial deformation. Which point is subject under maximum magnitude of axial deformation? E point, na? Is it correct? E point. Okay. So B point will be minimum. Okay. So this will be delta maximum axial deformation. This will be minimum axial deformation. Okay. So that means 1 minute. We have done our job, I guess. What happened to this? Yeah, just to remove it. Now, I think what is the objective? This is the objective. In this, what are the things you need to calculate? Axial stresses. Yeah. Here, what to do? Tell me. Axial stresses we need to calculate. Axial stresses in the members. Axial deformation at a point which is subjected under statically determinate prismatic composite bar. Okay, now composite means different materials. Compound bar means same material. Composite means two different materials. Okay, subject under uniform, or this is uniform, na? Only one load. Non-uniform means different loads. Statically determinate means you can easily determine the support reaction by using support reaction calculation. This particular equilibrium equations. Statically indeterminate means indetermined means both supports are fixed. One end is fixed, determinate. Statically determinate. Okay, na? Statically indeterminate. Determined or determinate actually. Okay? So that is the thing. Understood, na? Understood or not?
Yes, sir.
Okay. Now here, next we have drawn this simple diagram. Prismatic bar means uniform area of cross section. Prismatic bar subject under uniform axial loading condition with statically determinate bar. Okay, one end is fixed. Just you have drawn axial loading diagram. So that is first assume one direction. Start from here. Okay, na? Start from here and assume one direction, that particular sign convention. This is common for all the diagrams. Start from here, start from one end, finish at the another end. Focus only on the points. Don't focus on the portion. Okay. So start from here. I have seen the load. I have seen the load. Yeah, I have seen the load. Both are acting in same direction. Both are acting in the same direction means positive. Positive means you need to move up by P. Don't lift your pant until next load came. Now I'm here. I have seen the load. Both are acting in opposite direction. Then come down. Here you should know one thing. Sign convention must be perfect. After that, you need to start from one end and finish at the another end. Throughout the diagram, you need to follow the same sign convention. That is very important. I think hope you understood the content here. I think we have drawn that. What is the need of drawing this diagram? Understood na? Once you complete this diagram, you can write this member AB subject under this member AB na subject under the axial load P, BC portion 3P, CD portion 6P, and DE portion 4P. From this, you can happily calculate axial stresses in the different portions or members. Then you can calculate the axial deformation at a point. I think you understood one good point. Balaji, please tell me. Yeah, you asked a doubt. What is the member is made up of different material? What if? Okay, no issue. What if in the sense stresses won't change. Stress na independent of stress is independent of the material. Okay, it is depending on the load and area of cross section. Different material in the sense here. See this. In this case, total bar is made up. Cross section is A. Total bar is made up of E. Clear? So that is why you took E for all. Otherwise, here it is E1, it is E1, it is E2, it is E3, some material E4. Okay, same type of this particular same elastic modulus you need to take here. Here you will take E1. Materials are different now. Materials are different. Here you will take E1. Here you will take E2, E3, E4. Like that you will take. Correct or not? Understood, Balaji? Understood now? If cross sections are different. Here cross section is different. Okay. So in that case, you will take corresponding cross section. That's it. Here, if cross section is different, here it is A1. So that means like this only coming. Up to here it is like this. And after that, this kind of figure, A2. And then A3. It is A4. That you can solve tomorrow. Okay? So different area of cross section means corresponding area of cross sections you need to take. What is the shortcut for pen? No. Here it is A1, A2, A3, A4. That's it. Okay, corresponding diagram, loading. Length also different. L1, L2, L3, L4. Loads are different. P1, P2, P3, P4. That part you will incorporate while determine the axial deformation. Okay. So here loading na, anyhow from loading diagram you will get it. Not save. Now our diagram is safe. Clear? Any doubt, Balaji? I think, are you happy now? Today we have done some good job, I guess. Okay, na? This discussion is excellent actually. This part, na, I think it is really excellent. After that, you have drawn some materials. Okay, stress versus strain diagram. Then why steel is more elastic than rubber. Axial loading diagram, this just this particular chapter is started. Then we discussed about the objective. After that, we drawn axial loading diagram. Here also you have drawn axial loading diagram. Then you calculated corresponding stresses and axial deformations. That's it. Okay. So to entire chapter, depending on 2 points. One is axial stresses and axial deformation, corresponding axial loading. Next chapter, bending stresses, deflection. After that, torque loading, torsional stresses, angular deformation. That's it. That is Chinta material course. Understood now? What is the loading diagram and determine the corresponding stresses and corresponding deformations. Once you become expert in all the calculations and drawings and all the diagrams, then you are excellent in strength of material course. You will become expert in the all strength of material calculations. Okay, I'm done. Any doubts so far? Any doubts so far?
No, sir.
I think you understood the procedure to draw axial loading diagram. It is just a beginning. Don't worry.
So,
Okay, we need to draw so many axial loading diagrams, so many SFDs, BMDs, torque loading diagrams. All the diagrams I am following single procedure. Okay, now all the diagrams will be completed by one logic. Okay, there's logic. Start from one end, finish at the another end, follow the sign convention, and draw the figure in an appropriate way. Then do the calculations, corresponding calculations. Then you are the boss to strength of material course. Fine. Is it okay?
so what does the sigma h equal to 0 represent?
Sigma h equal to 0. Oh, that sum of the horizontal force equal to 0. This is equilibrium equation. Sum of the all horizontal forces equal to 0. That
Okay, okay.
sum of the right force equal to sum of the left forces. Okay?
Okay.
Fine. Good, good. I think we
Is
can
that a
meet tomorrow
condition
at the
given,
same
sir?
time. Thank you. Huh?
Is that a condition given or we are taking that?
No. It is equilibrium condition. It is fixed in the entire mechanical engineering. Sigma h equal to 0 for the
Oh, okay.
free body diagram. I think you have drawn free body diagram for the bar. For the free body diagram, you are taking sigma h equal to 0, sigma v equal to 0. In this case, you are not focusing on vertical loads. Even if you focus, nothing will happen. Okay, sigma v equal to 0 means vertical reaction is 0, bending moment also 0 here. Moment also 0, not bending moment, moment equal to 0.
Okay, sir.